Great. Thank you. Can you hear me?
Yes. Yeah.
Hi. Hi, Karen. Nice to hear your voice. So I'm really sorry, first of all, I couldn't be there in person. It's a great pleasure and an honor for me to be giving this talk in honor of Karen's mathematical contributions. Karen Smith has been a major influence on my career. Just to give you some examples, she was responsible for my first job talk, and then my first job, and then my second job, or maybe my third job. And then in between, she gave me really brutal feedback once on my first ever NSF grant application, which was extremely useful going forward. So thanks to Karen for all of that, but also more importantly, her mathematics has been a great influence for me. My thesis was on extending a vanishing theorem that Karen proved. Karen proved a vanishing theorem for the cohomology of ample and anti-ample line bundles. And my thesis was about extending it to slightly less positive bundles. And that was in 2010. And I spent the last 10 years of my career basically trying to extend that to mixed characteristic. And there were some detours into p-adic Hodge theory along the way, but that was always the ultimate goal. And so I was very happy to resolve this during the pandemic. And for me, this was an amazing mathematical experience, and it would not have been possible without Karen's initial work and questions that motivated the subject. So thank you very much, Karen. All right, so down to the business of today's talks, I want to talk about the Deligne-Du Bois complex. The Deligne-Du Bois complex is a certain complex of coherent sheaves that is important in Hodge theory and singularity theory and many other subjects. And I would like to explain by the end of the talk a new construction or a new perspective on this complex that comes from non-Archimedean geometry. But let me begin by sort of first just recalling what the object is before we do something fancy. So let me first recall the smooth case, which is the easy case of this story. So this is the algebraic de Rham complex of a variety. And for this one, K can be a field of any characteristic. So let's say K is a fixed field. Soon I'll specialize to characteristic 0. So if X over K is a smooth variety, then to such an X, Grothendieck associated its so-called algebraic de Rham complex, omega dot of X over K. And it's what its name would suggest. So the degree 0 term is the structure sheaf OX. Then you have the sheaf of 1 forms, 2 forms, etc. And the differential is the de Rham differential. And because of my assumption that X is smooth, these are locally free sheaves that show up. They're vector bundles. The differential is not OX linear, but that's okay. So this is the algebraic de Rham complex. And then the reason, or one reason why this is an important object to study is a theorem that Grothendieck proved about this. This was in 1966, I believe. So he proved that in characteristic 0, this complex computes singular cohomology. So more precisely, let's say if K is the complex numbers, then the algebraic de Rham cohomology of X, which is by definition the hypercohomology of this complex, is naturally identified with singular cohomology of the corresponding analytic space with complex coefficients. And so I think this is a rather remarkable theorem. If you think about the case where X is affine, then each of these is just it's a finite projective module over some commutative ring. And so as a complex, as a C vector space, each term is infinite dimensional. So the terms of this complex are highly infinite dimensional. Nonetheless, its cohomology by this theorem is very finite dimensional. So the theorem is suggesting that there's a lot of kind of cancellation happening, or the de Rham differential is very non-trivial. And it's quite a miracle, in my opinion. It also forms the starting point of Hodge theory. It gives you an algebraic way of accessing topological information about X, like the singular cohomology. It's controlled in terms of kind of algebraic differential forms. So for example, if X was defined over a much smaller field inside the complex numbers, like if it was defined over Q, then this gadget over here would also be defined over Q. And what the theorem would be saying is that there is a Q vector space whose base change to the complex numbers is identified with singular cohomology with C coefficients. Now, there's another Q vector space with this property, which is singular cohomology with Q coefficients. And the comparison of these two Q vector space structures is highly interesting from an arithmetic point of view. Other uses of the de Rham complex include vanishing theorems. It sort of lies at the core of many vanishing theorems, because ultimately we want to prove vanishing theorems for coherent sheaves. But the way we prove them is by sort of tweaking this complex and then appealing to vanishing theorems on the topological side. Versions of this complex in characteristic P are also very useful in characteristic P and p-adic Hodge theory, but I don't want to go there. In this talk, what I want to explain is what happens if you drop the assumption that X is smooth. And so let me move on to that case, unless there are questions. So I'm going to try and pause for questions. Please feel free to shout out questions. Okay, so I'm assuming that means no questions. Great. So the singular version of this is what's going to be the Deligne-Du Bois complex. Maybe I should first explain why it's not obvious what to do. I mean, you can certainly write down this complex I've written over here in the singular case. All the terms are well defined. It makes sense. But if X is not smooth, then omega-1 is not a very good object to consider. For example, it's not a vector bundle. The analog of Grothendieck's theorem will fail if X is singular. And so the usual de Rham complex is not quite what you want to consider. And there's a way to fix it. It goes back to Deligne's work in Hodge theory, mixed Hodge theory. And so that's why his name is attached to this. So DDB stands for the Deligne-Du Bois complex. And so let me tell you how this works. I think Shandor maybe did some version of this story yesterday. I will not spend too much time on it, but I want to tell you some key features. So from now on, K is a field of characteristic 0. And so I will summarize the existence of the Deligne-Du Bois complex in the following theorem. This is maybe from the late 70s. So fix some integer j bigger than or equal to 0, which is going to be the degree of the forms I'm looking at. Then the theorem says that there is a certain assignment. So then there exists a unique assignment which takes a scheme X, a finite type, over the complex numbers. So varieties, for example, but also it allows non-reduced structures for no extra work, and attaches to it a certain complex, omega j of X over K, underlined. And so this is a complex of coherent sheaves on X. It's not just a sheaf in a single degree, but it's a complex of such. And it comes with a comparison map from the usual sheaf of Kähler differentials. So I'll just call the comparison map alpha. So the usual sheaf of J forms has a map to this underlying version, the Deligne-Du Bois version. And what makes this assignment unique are two normalization properties, or two properties. So such that A is a normalization axiom, which says that in the smooth case, nothing changes. So alpha is an isomorphism if X is smooth. And property B is essentially saying that once you know what happens in the smooth case, you can figure out what happens in general by explicit recipe. So this recipe goes by the name of CDH descent, but it says something very concrete. So let me spell out the concrete version of it. Given a proper map, so given a map, let's say pi from y to, or sorry, let me write it as follows. Given a Cartesian diagram, which looks like so. So I'm going to have X to Y, Z, I inside Y, and then E is going to be the preimage of Z. Let me give this map a name. I'll call this pi. So the assumptions are going to be pi is proper, I is a closed immersion, and crucially, pi is an isomorphism outside Z. So imagine you're just blowing up Z. So these are such squares, commutative squares are called abstract blow-up squares because they abstract the properties that a blow-up has. And the condition is that given a Cartesian diagram like this, the Deligne-Du Bois construction takes this to an exact triangle. So the natural maps give an exact triangle. Of sheaves. So the object you might be interested in understanding is the Deligne-Du Bois complex of Y. It maps to the push forward of the corresponding object for X, and also the push forward of the corresponding object for Z. And both those guys map to the corresponding object for the exceptional guy. So let me give this map a name. It's G. RG lower star omega J E. Oops, I ran out of space. And the claim is that this is actually an exact triangle via the natural map. And so this is kind of the main existence theorem, or if you like, it's even a definition of this object, of this Deligne-Du Bois complex. It's characterized by these two properties, and you can turn that into a definition if you like. And I want to spend some time today unraveling what this object is, and then giving you a non-Archimedean perspective on it. So this theorem is about to scroll off the page. I'm about to give you a couple of examples, but are there any questions before it scrolls off the page?
No
Okay,
questions.
so let me. Yeah. No questions. Okay. Let me give you an example. So I said over here that I can work with schemes rather than just varieties. And so let me first tell you that this was not important in the sense that the Deligne-Du Bois construction does not care about the scheme structure, but it's still useful to have it in inductive arguments. So let's say X is, or let me say it this way, X reduced to X induces an isomorphism on Deligne-Du Bois complexes in the sense that omega J of X is isomorphic over K, is isomorphic to Ri lower star omega J of X reduced over K. So the theory doesn't care about nilpotents, and it's very easy to see where this comes from. You just apply this CDH descent axiom in a degenerate case. So consider, proof is to just consider the Cartesian diagram given by X reduced, X reduced, X reduced, mapping to X. So this is a square that satisfies the axioms in CDH descent, and so then the CDH descent axiom tells you the conclusion I wrote down. So it doesn't care about nilpotents, but at the same time, it is defined for them. And so now let's see why that's useful. So the sort of standard example to keep in mind for what the Deligne-Du Bois complex looks like is the case of a cusp. So let's say X is the vanishing locus of y squared minus X cubed inside A2. And pi is the normalization map. So pi is a copy of A1, and the coordinate on that A1 is y over X. And so then the claim is that in this case, all the Deligne-Du Bois terms, but they're only interesting for j equals 0 and 1, is identified with the push forward of the Deligne-Du Bois complex of y. Okay, and so maybe I won't prove this for you, but I'll leave it as an exercise in basically running the CDH descent axiom and then using example A. Example A tells you that the scheme structure doesn't matter, and if you take y to be a cuspidal curve and x to be its normalization, then what you'll get over here is a copy of the spec K, and over here you'll get a non-reduced version of spec K, but these two have the same Deligne-Du Bois invariance, and therefore these two will as well. So this is what the object is. And as you can see, it's pretty computable in examples if you know explicitly how to relate your singular variety to smooth varieties. But there's something maybe slightly dissatisfying about this theorem or this construction, which is that it feels more like it's constructing an object or it's telling you how to compute an object, but it's not quite an intrinsic definition of the object. And so part of the goal today is to actually give you a direct intrinsic definition, and then this will be like a theorem about that definition. Okay, so any questions about what the Deligne-Du Bois complex is? I will tell you why you should care about it in a second, but before I scroll things off the page, again, I'm happy to take questions.
No questions.
Okay, thank you. Okay, so why should you care about this? I mean, there's probably everyone that thinks about this has their own reasons to care about it. Let me offer 3 arguments. So first one is Hodge theory, which is the reason this was devised. So now it allows you to say a version of Grothendieck's theorem without the smoothness assumption. So now if x over k is any variety, then the hypercohomology of this Deligne-Du Bois complex. I guess I didn't say it, but there's also a differential on these complexes relating the I forms, the J forms to the J+1 forms. Is naturally identified with the singular cohomology of x with C coefficients. And moreover, since the left-hand side is the hypercohomology of a complex, you can sort of look at the filtration of the complex given by forgetting terms of the complex. And that gives what looks like a stupid filtration on this complex, but at the level of hypercohomology is an interesting filtration. And that's, in fact, the Hodge filtration of mixed Hodge theory in the proper case. So let me just say with naive stupid filtration of this Deligne-Du Bois complex giving the Hodge filtration of mixed Hodge theory in the proper case. So just like the classical Grothendieck theorem, this gives you an algebraic way to access the singular cohomology of now possibly singular varieties. And this can be useful. Another reason to care about this is in relation to singularities, and that's closer to the theme of this conference. So having access to these complexes allows you to define a whole new bunch of invariants and therefore classes of singularities. And so let me just recall the classical one. So a variety X is said to have Du Bois singularities if the degree 0 part of the Deligne-Du Bois complex is the structure sheet. So as Du Bois singularities if this comparison map from OX to omega 0 underline X is an isomorphism. So at least for like 0 forms, nothing funny has happened. And this turns out to be a rather interesting and well-behaved class of singularities. So let me give you some examples. I won't prove these. So nodal curves are Du Bois. And I just told you earlier that cuspal curves are not, because I computed what the Du Bois complex in degree 0 was in that example. Another class of singularities as Du Bois is log canonical. So this is a theorem of Kolar and Kovács. So log canonical implies Du Bois. And it's easy to also write down singularities that are not Du Bois, but not like normal singularities that are not Du Bois, just by taking suitable cones. So it seems like an interesting class of singularities that can show up from many different perspectives. And recently, there's some work on trying to understand higher versions of this condition. Essentially, this was just concerned itself with the degree 0 part of the Deligne-Du Bois complex, but you can wonder what happens if you tweak that index to other indices. But that theory is still being sort of developed, and I won't talk about it. And then maybe a third reason to care about it, closely related to Karen's ideas, is the connection to characteristic P. And so here there's a conjecture, and I believe this conjecture is due to Schweid, but he is in the audience, so you can correct me if I'm wrong. And the conjecture is essentially, I'll just state it informally, that X is Du Bois, or X has Du Bois singularities, if and only if the X mod P is F injective for infinitely many P. Infinitely many P. So some care has to be taken on what it means to reduce X mod P. This doesn't literally make sense as written, but there's a standard way to do it. And so this is a very interesting conjecture because it's connecting two invariants of very different origin. Right, the left-hand side is somehow defined basically by resolution of singularities and some recipe built off on top of that. And then the right-hand side is defined in terms of the Frobenius action. And for no a priori reason, the two should be related to each other. And so let me just say that this conjecture, this direction of the conjecture is known. And Carl proved it. And this direction is known under a strong arithmetic conjecture. So something called the weak ordinarity conjecture, which is a conjecture about smooth projective varieties. It essentially predicts the existence of lots of primes where Frobenius acts in a certain way on cohomology. And so I think this was inspired by Karen's work on an analogous theorem about KLT singularities. And it's a highly interesting area of study these days. Okay, so these are some reasons you might want to care about the Deligne-Du Bois complex. What I want to do next is tell you how this shows up in non-archimedean geometry in a very natural way, one that doesn't a priori involve talking about resolution of singularities. So now we're going to go into the non-Archimedean land, unless there are questions. I'm happy to answer questions as always.
No questions.
Okay, thank you. I think that was Kevin, right?
Ray.
Oh, whoops, Ray. Hi, Ray. Review of non-Archimedean geometry. And so I'm going to stick, this is in characteristic 0. So I'm going to, everything equal characteristic 0. So nothing p-adic going on. I'll explain the p-adic motivation at some point. So K is going to be a field of characteristic 0. Feel free to take it to be the complex numbers if you wish. And capital K is the ground field I'm going to work over, which is supposed to be a non-Archimedean field. So I'm just going to do the simplest non-Archimedean field one can work with, which is K Laurent series T. So this means you take K, you do formal power series in one variable, which is a DVR, and then you invert the variable to get a field. So this is a discretely valued field because it comes with a discrete valuation inherited from the discrete valuation ring KT. In particular, it has a norm on it. So there's a notion of size. And things that are divisible by big powers of T have small ties. That's how the norm is works in practice. But because it's a field with a topology, with a metric, with the notion of size, it makes sense to do not just algebraic geometry over it, but also some kind of analytic geometry over it. And this was done by Tate in the 60s. So Tate, I think starting in the 1962, but the paper appeared much later, explained that there's actually a very nice category of analytic spaces over K. So there exists a category called RSK, which is of rigid spaces over K. And it has lots of nice features, some of which I'll recall. It's rigid or rigid analytic or analytic. I'm gonna be a little sloppy about which terminology I use. And one feature of this category, just like any category, just like the category of complex analytic spaces, is that it comes with an analytification functor. So plus a functor, which takes a variety over K to a rigid space over K. And the functor behaves like the analytification functor in complex geometry. So it's, it doesn't kill anything. And on proper objects, it's fully faithful, etc. And so it will take me way too far afield to actually define what a rigid space is. And I'm just going to tell you some key features that rigid spaces have that are relevant to our discussion. So I'm going to make some extended series of remarks on rigid spaces. And so actually, maybe I should also say that for experts or people that already know this stuff, when I talk about rigid spaces, I'm secretly thinking in the language of adic spaces. There's many different formalisms of rigid spaces. I mean, Tate initiated one of them, and people refined it over the years. And the one I'm using myself is adic spaces. but I don't think this will be in the foreground very much. Okay, so let me tell you a little bit about this category. What do the objects look like? So first of all, just like algebraic geometry is built out of affine varieties, the analogous building blocks in rigid spaces are called affinoids. And I'll give you the key example. So the building blocks are affinoids. I think they're called affinoids just because the term affine was taken. And so the example, the most important example is the closed unit disk. So it's usually just called D, or if you want to specify the radius, which is 1 right now, I'll say D01. This is the closed unit disk of radius 1 around 0. And so what does it look like? Well, so now you have to go into the specific formalism of what kind of spaces you're talking about. But what's formalism independent is what are the points in the space. So let me tell you what the K points are. And the K points are exactly what the name would suggest. So they are all elements of the ground field K, which have absolute value less than or equal to 1. And if you remember how the norm on a non-archimedean field works, this is exactly the ring of integers, OK, inside K. So this was, I remind you, it was this DVR K power series T. Another thing I can tell you about this space is that since it's affinoid, it corresponds to a ring. And so let me tell you what the ring is. So the ring of functions on D, so D is, in fact, D is a spectrum of a certain ring, spectrum in this analytic sense now. And the ring R is the following ring. So essentially, you write down the obvious analytic functions you could imagine on a closed disk of radius 1. So they should be power series that converge on that ball. And algebraically, it turns out to be the following. So you take OK, this DVR that you're starting with. You join a variable z to get just the polynomial ring in one variable. This would be functions on affine space. But you want the functions to converge whenever z is less than or equal to 1. You don't care what happens outside. And so that corresponds to doing a t-adic completion here. And then since we're working in characteristic 0, or t over the fraction field, we have to invert t. So this is the ring of functions on the closed unit disk of radius 1. And it's a pretty nice object. It's a Dedekind domain. I think it's even a PID in this case. So these rings of rigid analytic functions are quite simple objects. Or rather, they're tame objects. They're not weird rings. They're Noetherian, Jacobson, excellent, blah, blah, blah. And then you can do n variable versions of this and then closed subsets of this and so on. You can imagine how algebraic geometry is built up from affine varieties, and you just try to replace the word affine with affinoid at every step. Okay, so that's what the affinoids are. I'll tell you a little bit more about the global structure of these rigid spaces. So any rigid space X over K has a coherent structure sheaf. So there's a good theory of coherent sheaves on these spaces. Structure sheaf OX. But it has good properties. So with reasonable properties, similar to what happens in algebraic geometry. And just to give you a sense of what I mean, let me mention 2 of them. So first of all, if X is the analytification of a variety and the variety is proper, then there's a Gaga theorem. So then dB co of Y is the same as dB co of X. Sorry, this was X and this is Y. So this is similar to what happens in complex analytic geometry, where in the proper case, analytification doesn't lose information even about coherent sheaves. And the second property is that in the affinoid case, which is the opposite case, you just get modules over the corresponding ring. So dB co of R, or dB co of X is dB co of R. And I again remind you that R is a nice ring. It is Noetherian, excellent, Jacobson, etc. So it's reasonable to think about coherent modules over it, which is finally generated modules. So far, I'm telling you everything works just like it does in algebraic geometry, and there's one more item along these lines, and then I'll tell you something funny that happens. So essentially, a consequence of property 2 and a little work is that any rigid space has a reasonable theory of differential forms. And again, it works like in the algebraic case. So good in the sense, like the same way the usual notion of differential forms was good in algebraic geometry. So it was good in the singular, good in the smooth case, and a little funny behaved in the singular case. But you can do the same argument that Deligne-Du Bois did to fix it, and you get a notion of Deligne-Du Bois complexes in this setting. The same theorem I've written down earlier remains true in the analytic category. So you may build these Deligne-Du Bois complexes, omega j underline x over k as before. Maybe one thing I didn't say that's implicit here is that even in this analytic category, we know resolution of singularities. So in here 6.0, we know resolution of singularities not just for varieties, but also analytic spaces. And so then you can really run the same argument you used to write down the Deligne-Du Bois complex in algebraic geometry. And these complexes have the same kind of properties that the algebraic ones do. And if X was the analytification of a variety, these complexes would be the analytification of the corresponding sheaves, etc. So far, no surprises. I'm just saying there's a good notion of analytification, and it reflects everything we know from algebraic geometry. Well, before I tell you the funniness, any questions?
Can I ask a question?
Yes, please.
Is the notion of coherent sheaf on an aphanoid just defined by pulling back from the what am I trying to say? I'm just wondering how you define the coherent sheaves on X.
How you define them? I think they are basically defined so that this theorem is true.
Okay. Yeah, that's what I was basically asking.
Yeah, like the hard work goes into proving that these rings have good properties. Like maybe here it's not so surprising because I took something Noetherian, adjoined a variable, and did completed localizations. But actually, for many applications of rigid geometry, you want to allow K to be not just this field over here, but possibly its algebraic closure. And for the algebraic closure, the ring that shows up over here is not a discrete valuation ring anymore. It's a valuation ring whose value group is divisible. And so the ring that would show up over here would not be Noetherian. And so then the fact that it becomes Noetherian after inverting T is like a non-trivial theorem. And that's really what's making this work. Is that okay?
Yeah, thank you.
I have a question, sorry.
Yep.
How do you make those new work things a complex? Like how do you define the map in the same way as we do in the previous setting?
Sorry, I didn't follow the question. Which complex are you talking about?
The new omega j bars. How do you define maps between them? Is it in the same way as you define in the Du Bois complex previously?
Yeah. I'm saying the theorem I wrote down earlier is also true in rigid spaces, and the differentials also work out the same way. Sorry, is that okay?
Yes.
No other questions.
No other questions. Okay, great. So now let me tell you about something funny that happens in this world, which is where we were going to get some mileage from. So for any rigid space X, in addition to the structure sheaf, there is another sheaf floating around. So on any, on any rigid space X over K, we have a natural integral structure sheaf. I have an integral. I'll call it integral because the name comes from p-adic Hodge theory, where integrality means usual integrality. Now it's just formal. So there's a natural integral subsheaf. OX plus is what it's usually called, and it sits inside OX. And so this is very easy to define. OX plus evaluated on an open U is going to be those functions defined on U with the property that their absolute value is less than or equal to 1 at every point. So at every point of a rigid space, there's a notion of size. And so it makes sense to ask whether or not the value of that function is less than or equal to 1. And so this is now a sheaf of OK algebras, but not K algebras. So it's over the DDR rather than its fraction field. That's what makes it integral. And this sheaf has some nice properties and some surprising properties. So let me tell you first what it does in the simple example. So let's go back to the example of a disk. You can ask, what is OX plus of the disk itself? So let me remind you what OX of a disk was. So the disk was defined to be the adic spectrum of this ring R, where R was you take a polynomial ring OKZ, you t-adically complete it, and then you invert T. And now if you think about what it means for a function to be less than or equal to 1, well, more, you'll see that it just means that you're not allowed to invert T. So the output over here would just be a completed polynomial ring over the DVR. And so in some sense, it allows you to extract kind of natural invariance where T is not inverted, attached to something, a space which lives in a world where T is inverted. And so now let me tell you why this is funny. So let me give a couple of warnings about this. So I say funny just because there's no kind of model for it in algebraic geometry that I know. And so here's one funniness of it, which is if you take OX plus and you evaluate it on A1. Sorry, I didn't tell you. Sorry, I was meant to give this example earlier of what A1 was. If you allow me, I'm going to squeeze it in here. Sorry, this was example 1, and let me squeeze in example 2 over here. Because it's rather short, but just illuminating. So A1 is an algebraic variety, and it makes sense to analytify it. And you can ask, what is it in this rigid world? It's not the disk, because there's no constraint on what the size of the point is. But in fact, it's just a union of disks. So it's the union of all integers R of disks of radius R centered at 0, which is, of course, what you would expect. But importantly, because this is an infinite union, the space is not quasi-compact. Whereas these aphenoids are always quasi-compact. So from this non-Archimedean point of view, algebraic varieties which are not proper are rather large, and these aphenoids are much smaller, much more tame versions of them. And so that's going to get reflected now in a second. So I told you that OX plus evaluated on the closed unit disk, which was an aphenoid, was a nice ring. It was a completed polynomial ring. But what happens if you evaluate it on A1? Well, now you're supposed to give functions on A1 that are bounded by 1 at every point. If you remember complex analysis, you would think that there are no such functions. And that's in fact true. So this is just K. Because by Liouville's theorem, any entire function that's bounded should be constant. And so this is a non-Archimedean version of it. Another funny feature, and this is directly relevant to the Deligne-Du Bois discussion, is what happens for a cusp. So let me discuss that. So let's say X is the vanishing locus of y squared minus x cubed, and I'm going to imagine it sitting inside 2 copies of the disk, rather than 2. I mean, it could be sitting inside A2, but I'm just thinking of it's the usual picture where if you imagine this is A2, then this is D2 inside of it, and then the cusp is something like that. And so what happens for OX plus of a cusp? So 2 things. First, OX plus itself of X is not so surprising. It's the ring you would naively expect to write down in this situation, which is you adjoin y and x. You set the relation y squared minus x cubed. you t-adically complete everything, and you invert t. These are kind of the natural functions that would make sense on the closed unit two-ball, which is D, and they're only you only care about their values on the curve, so you mod r by this equation. But what is surprising is what happens for OX plus mod t to the n. So, question?
You shouldn't invert t here, right? You're doing plus.
Thank you. Yes, thank you. Yeah, I'm doing OX plus and no inverting t. Other comments or questions? So
no other questions.
Thank you. Right. So the normalization of x is a1 like before, and the x is itself not normal, and the reason it's not normal is that the function y over x doesn't make sense on x, but it does make sense on the normalization. So let me emphasize this. So in this case, there's no such thing called y over x. Yeah. So it's just another way of saying that this is not normal. But what's surprising maybe is that if you take OX plus, you reduce it mod t to the n. Remember, this is a sheaf of OK algebra, so it makes sense to reduce it mod t to the n. And then evaluate it on x. Then, in fact, y over x does make sense. And this is for any n bigger than or equal to 1. Okay, and so let me give you just some intuitive argument for why this works. Zoom in to this picture. This is one advantage of giving a Zoom talk. Okay, so you're trying to make sense of the function y over x on this cusp. So what I'm going to do is I'm going to say, okay, if I'm not at the origin, then the function y over x certainly makes sense. It's just, well defined. And if I'm in a sufficiently small neighborhood of the origin, I'm just going to take 0. And why is that a good thing to do? It's because y over x, at least in the normalization in the polynomial ring, it's a variable. And so if you're sufficiently close to 0, the variable's values are sufficiently close to 0, which means it vanishes mod t to the n. So this is just the observation that you glue y over x away from 0, or on x minus 0 to 0 in a very small neighborhood of 0. And the notion of smallness depends on the integer n. Okay, and so what's going on over here is that OX plus of x reduced mod t to the n is not the same as OX plus mod t to the n of x. There's a sheafification a priori involved in computing this object, and this is saying that this sheafification is actually doing something non-trivial. So another way to write this is h1 x OX plus as t to the n torsion for all n. This is just by chasing the log of multiplication by t to the n. And so what this suggests is that if you want to maybe extract something closer to the Deligne-Du Bois complex, you might want to work with these truncated versions of OX plus rather than OX plus or OX. And that's what the main theorem is going to be. But are there any questions now?
No questions.
All right. So, question? Yeah. Okay. So I want to turn this example into a theorem, and it works out surprisingly nicely. So main theorem. So the setup is the same as before. K is little k, Laurent series T, characteristic of little k is 0, and x over k is any rigid space, possibly singular. So I want to extract certain mileage out of the fact that these sheaves are larger than we would naively expect them to be. And here's one way to do it. So definition. I'm going to consider their completion, so the inverse limit over all n. So OX plus hat is the derived inverse limit, because I'm working with sheaves of OX plus mod T to the N. And so this is now just a complex rather than a sheaf in degree 0. It's a complex of OX plus modules. And OX hat is what you get from this by inverting T. So this is a complex of OX modules. And there are similar variants for sheaves of differential forms, which maybe I don't spell out, but I'll just say. And similar variants for omega j at x over k for all j, and the plus version, but okay. And so maybe one word about these objects is there's a setting in which these objects have been considered before, which is if you work over p-adic fields. So k is not an equal characteristic 0 non-Archimedean field, but rather a p-adic field. And you don't just work with the underlying topological space of X, but you work with this, what's called the pro-étale topology. Then these objects have been considered before, and they're in fact called the completed structure sheaves and completed integral structure sheaves on the pro-étale side. What happens in that world is that they're actually in degree 0. They're honest sheaves, and that's basically has to do with the fact that there was a pro in the site. But other than that, I believe I don't think this has been considered in non-Archimedean geometry in characteristic 0 before. And maybe the reason is that the following theorem is true, which I think is also, I believe it's not known. I would be very happy to find out otherwise. So the theorem is that these completed structure sheaves are exactly the Deligne-Du Bois complexes. So omega j hat x over k is canonically identified with omega j underline x over k for all j. And so this is what I meant when I said I wanted to give a non-Archimedean construction of this Deligne-Du Bois complex. The way this object is defined, like this is what the definition is for j equals 0, it doesn't really involve thinking about resolutions of singularities. It involves doing something kind of intrinsic on a fixed adic space, which is X, but then the output seems to be related to something that you would usually do using resolution of singularities. So I want to make some remarks about this theorem next. So the first remark is that the j equals 0 case, at least, also works over p-adic fields. And this was actually my original motivation for pursuing this. There was people didn't know what these objects look like over p-adic fields, and there were some claims in the literature that were a bit too strong, and they're related to the fact that you're supposed to see Deligne-Du Bois complexes and not just the usual de Rham complex here. I expect the higher J versions are also known, but the proof I have uses resolution of singularity, so it's certainly or for the integral models, and so it wouldn't work in the p-adic case. And the second remark is, let me just spell out what this theorem means concretely about the cohomology of OX plus, because that was, as I said, the original motivation. So the j equals 0 case implies the following. If X is affinoid, then HI X OX plus has unbounded T torsion, which means the T torsion is not killed by a fixed power of T. It goes to infinity if and only if HI minus 1 of the Deligne-Du Bois complex in degree 0 mod the obvious part, mod the structure sheaf is non-zero. So as soon as you see a non-Du Bois singularity on your rigid space, you should have expected to see this unbounded T torsion. And the example I did of the cusp was maybe just the simplest example of this, because I said this H1 was 0 for all n, and that corresponds to the fact that X is not normal, or not Du Bois. Okay, so I have about 9 minutes left. I actually don't have that much material, but let me just make a comment on the proof or what the key points of the proof are. There are just two of them that I want to emphasize. So key points, key ideas of the proof. So the first one is related to this sheaf OX plot, and I told you that it was kind of funny, and here's another way in which it turns out to be funny. So if you take OX plus, reduce it mod t or mod t to the n, and then compute stocks at a point x, it turns out to only depend on the residue field at that point. So this only depends on the residue field. So this suggests that the sheaf OX plus mod t to the n behaves like it's more topological in nature. It doesn't care about nilpotence, for example. And this is also how you prove that it has blow-up descent or CDH descent. And I guess so far I was fairly agnostic about what kind of analytic spaces I was working with. But for this theorem, at least, I think it's important that I'm in the Huber's world of adic spaces. Because I'm talking about points, and it's usually not a good idea to talk about points in the sense of Tate. His Grothendieck topology doesn't have enough points. Okay, and then the second thing I want to emphasize is that there's a Riemann-Zariski point of view on adic spaces, and that's what gets used in the proof. So if my aphenoid X is the adic spectrum of some algebra R, which is obtained from some integral algebra by inverting T. So with, let's say, R over OK, topologically a finite type. So this means that it's the T-adic completion of something of finite type, say. Sorry, it doesn't mean that, but it's implied by that. So then this adic space X, together with the structure sheaf OX plus, has a very nice description, which has the Riemann-Zariski flavor, which is it's the inverse limit of y hat, where y to spec R is a T admissible blow-up. Well, let me just say what it means rather than define it. So it's a blow-up at an ideal containing a power of T. Some large power of T. And the hat indicates I pass to the T-adic completion, so regarded as a formal scheme. And this equality is an equality in locally ring spaces. So this is in locally ring spaces. And for this, it is certainly crucial to work with Huber's adic spaces. And essentially, because of this theorem, you can translate whatever assertions I'm making about adic spaces into assertions about these blowups of spec R. And then you have tools from algebraic to tackle those. So resolution of singularities and analysis of differential forms under blowups gets used in proving the theorem. Okay, I think this is all I wanted to say, and I'm done a few minutes early. So thank you for listening to me.
Any questions? What do you expect to happen with this, say for maybe a p-adic field or a characteristic p field? Would this compute something like the analog of Du Bois singularities in characteristic p, or something like F-injective singularities in characteristic p?
I'm not 100% sure, but I suspect it would be like Du Bois singularities. Like there's some invariance you can define by just using this definition of CDH descent. Even in characteristic P, you can define a notion of Deligne-Du Bois complexes via CDH descent. Unless you know you have resolution of singularities, these are hard to control. But if you assume resolution of singularities, then I think the picture should be quite analogous to what happens in characteristic 0. So I think you would not see the Frobenius here.
Any other questions?
So hi Bhargav. So does this tell you anything about like Du Bois singularities or higher Du Bois singularities, or like they have various features like injectivity theorems, Chandra and I proved or anything like that. Or
Right.
various things like Nurture proved or.
Okay, so and thanks for the question. So maybe I should have emphasized this, that I'm still thinking about this stuff.
Okay.
And there are various things I want to sort out. Like one of the most urgent things to me is that I really don't like the restriction to discretely valued fields. I'm gonna get rid of that. But yeah, there are some statements along the lines you asked for. I don't have the most general statements, but for example, there is a statement that if you look at, don't know if I'll be able to reproduce it, but I think there's this theorem, right? So my understanding is that it's always true that omega I underline lies in the derived category in degrees less than or equal to I, and omega 0 is actually, there's like one better. And so I think this, and then there are versions of this for higher forms if you put more conditions in the dimension. And so I think this kind of statement falls out very easily from this definition, essentially because it's being computed in terms of the, well, I mean, it's essentially this theorem over here. I'm sorry, like it falls out of this. So if you want to control the cohomological amplitude of this, or equivalently the quotient, you need to control the cohomology of OX plus in one higher degree. And X is a spectral space of dimension equal, the same as the dimension of X. And so there would be nothing in D plus 1 over here if you're interested in D over here. So there are some soft arguments like that. But I don't have any more precise statements yet.
Thanks.
Any other questions? Well, if we have no more questions, we should thank Bhargav again.